At 25,000 feet above Nazi Germany, the sky was eerily still. The sun hung cold and distant, and every breath Jack Reynolds took through his oxygen mask felt like inhaling ice. His fingers were stiff on the control stick. The metal around him groaned from the pressure change, and ice crystals floated in the canopy like slow-moving snowflakes. Behind him, a twin-engine Messerschmitt Bf-110 closed in quickly, its heavy frame gaining just enough speed to become a threat. Jack yanked the stick back and climbed higher, pushing the limits. Most American fighters would have sputtered and stalled at this altitude. The air was thin, engines overheated, cooling systems couldn't keep up. But Jack's P-51 Mustang surged forward like it was just waking up. The Merlin engine under the hood purred instead of straining, pushing past 25,000 feet without a hitch. Jack couldn't explain it, but he felt it. This plane was different. It held together when every other aircraft would fall apart. The German pilot tried to follow, climbing after Jack. His aircraft wobbled, stuttered, and then slipped out of the climb. Falling away into the blue, Jack let out a half-laugh, half-breath, his heart pounding against his oxygen mask. This wasn't normal. This Mustang didn't fly like the others. It wasn't in the manual. The airframe looked the same, the engine had the same markings, but something somewhere had changed. What Jack didn't know, and what no one could see, was that the edge, the advantage, had started far below. Not in a factory, not in an office, but in a freezing hangar in East Anglia, England, where one American mechanic made a decision that broke all the rules and may have saved Jack's life. The story begins in 1942, when American military leadership was selling a dream. The P-51 Mustang wasn't just another fighter. It was the future, sleek, fast, long-ranged, and powered by the British Rolls-Royce Merlin engine. Hailed as the perfect answer to Nazi Germany's Luftwaffe, it was officially deemed flawless. Training manuals praised its engineering. Public speeches boasted words like revolutionary and invincible. It was presented as the ideal aircraft that would dominate the skies. But down in the muddy, wind-swept airfields of East Anglia, perfection was nowhere to be found. The Mustang looked great on paper. It flew well in warm weather at low altitude and under controlled test conditions. But in real combat, at altitudes of 20,000 feet and higher, in sub-zero air with full throttle pressure, pilots and mechanics began to notice the truth. The aircraft had a hidden weakness. The cooling system in particular became a serious problem. The belly-mounted scoop under the fuselage was supposed to solve everything. It was designed to draw in high-pressure air to cool the radiator, allowing the engine to run at full power longer. Engineers had even experimented with the idea of using airflow to generate thrust, a theoretical phenomenon called the Meredith effect. But in practice, the system was finicky. If the airflow wasn't perfect, temperatures skyrocketed. Pilots began reporting engine overheating during climbs. In the middle of dogfights, their gauges would spike red, warning them to throttle back or risk burning out. In winter, the coolant sometimes froze in the lines before the engine could even warm up. And if any part of the pressurized cooling loop leaked, it didn't take long for the engine to seize or catch fire. But the official stance from command was clear. Do not modify the aircraft. Do not question the design. Follow procedure. This answer didn't sit right with a 33-year-old staff sergeant from Tulsa, Oklahoma, named Melvin Harper. Everyone on base called him Tex. He was a lanky, soft-spoken mechanic with hands like steel vices and a mind that never stopped tinkering. Before the war, he spent his weekends tuning flathead Fords and drag racing friends down old farm roads. He didn't care much for rules, but he knew machinery intimately. Tex had been assigned to a fighter group stationed at a former Royal Air Force field outside Cambridge. Cold winds tore through the open hangars, and the concrete froze every night. He and his crew worked 12-hour shifts, sometimes longer, keeping Mustangs running through frost, wind, and mud. Over time, something began to bother him. The sound. The hollow metallic groan the engine made when climbing quickly at high altitude. Tex didn't like it. Then came the complaints. Engine temperatures too high, coolant systems needing constant repairs. More than one Mustang came back scorched under the cowling or didn't come back at all. Tex read every manual, cross-checked every detail. And then one night in December, after yet another overheated P-51 limped back from patrol, Tex crouched under the fuselage with a flashlight, studying the belly scoop. He started asking questions no one else dared ask. What if the scoop's angle was wrong? What if the airflow didn't compress the way the designers thought it would? And what if reshaping the inside of the duct could make the radiator work better, cooler, cleaner, more efficiently? Officially, he was supposed to log the issue and wait for updates from stateside engineers. But Tex had lost 2 friends that week. He wasn't about to wait. So he made a decision. The next morning, armed with tools and the knowledge of how machines really worked, Tex set to work modifying the scoop, reshaping it to improve airflow and prevent the overheating that had plagued the P-51s. He wasn't supposed to do it, and it could have cost him his job or worse, but he did it anyway. What happened next would save countless lives and change the course of history in the skies over Europe. With scrap aluminum, a welding torch, and a mechanic's instinct honed by years of racing engines under pressure, Tex Harper broke the rules. He didn't ask for permission. He didn't file a report. He just got to work, and in doing so, he set off a quiet revolution. It didn't start with a general's order, but with a mechanic's idea in a cold hangar in East Anglia, England. The unapproved fix. Tex Harper didn't just see a problem. He felt it in his gut. He heard it in the way the engines strained at high altitudes, saw it in the temperature charts. He knew the cooling system wasn't doing its job. So instead of waiting for orders or filing another complaint, he rolled up his sleeves and tackled the problem with the tools he trusted: a hacksaw, a rivet gun, and a lifetime of mechanical know-how. Tex started by removing the lower access panel. Beneath the belly scoop of a P-51, inside, was the radiator duct, the system, designed to channel outside air to cool the engine. It seemed fine on paper, but Tex wasn't convinced. He believed the internal shape wasn't optimized for high-speed, high-altitude flight. If the airflow was directed correctly, it wouldn't just cool the engine. It could even generate a small amount of jet-like thrust. That was the Meredith effect, an idea first proposed by engineers at Rolls-Royce, but never fully implemented. Tex didn't need to read any white papers. He understood how airflow worked from his time around drag races and custom cars. What he saw inside that scoop made him shake his head. Sharp corners, misaligned joints, and no smoothing to guide the high-pressure air where it needed to go. The duct wasn't helping. It was holding the plane back. So Tex made a decision. Using thin sheets of polished aluminum from a damaged wing panel, he cut and shaped internal vanes, angled plates that narrowed the airflow passage, forcing the incoming air to compress before reaching the radiator. He smoothed the edges, riveted the pieces in place, and added a makeshift seal around the access hatch to reduce turbulence. Tex didn't tell his commanding officer. He didn't log the modification. He didn't even mention it to the pilot scheduled to fly the aircraft the next day, Lieutenant Jack Reynolds. Jack was a younger pilot in the squadron, brave, sharp, and just cocky enough to push a Mustang to its limits. When he climbed into the modified plane the next morning, he didn't know anything had changed. But 30 minutes into his high-altitude patrol, Jack radioed back with an odd report. Birds climbing smoother than ever, temps holding steady. "Is this a new engine?" Tex didn't answer. He just smiled. By the end of the flight, the results were clear. Engine temperatures at 25,000 feet were 15 degrees lower. The climb was noticeably faster. Jack said the plane felt tighter, more alive. He didn't know why, but he liked it. Tex didn't stop there. Over the next 2 weeks, he applied the same mod to 6 more Mustangs, each time tweaking the ducts based on what he'd learned. He refined the angles, reduced drag, and tested different sealing methods with parachute cloth and adhesive resin. The impact was undeniable. Planes with Tex's mod climbed faster, stayed cooler, and returned from missions with fewer mechanical failures. Pilots began requesting the hot planes, Tex's planes. They started calling the tweaks Harper's hacks. Unofficially, the squadron commander gave Tex the green light. Officially, nothing had changed. There was no paperwork, no authorization, just results. Other crews took notice. Mechanics from neighboring squadrons started asking questions. "Hey, mind showing us what you're doing with your scoops?" Soon, Tex was sneaking into Tex's hangar at night, measuring ducts and sketching designs on cigarette packs. The mod spread like wildfire and no one dared report it. After all, the pilots flying these machines had a simple motto. Anything that brought them home alive was worth keeping quiet. Tex knew he was walking a fine line. He wasn't just altering military hardware. He was doing it during wartime, without approval. If anyone in command found out, he could be demoted, court-martialed, or worse. But for Tex, it wasn't about the rules. It was about survival. The turning point came in mid-February. One of the base's best pilots, Captain Roy "Red" Lansing, flew a mission deep into occupied France in one of Tex's modified Mustangs. During the flight, Red was ambushed by 3 Focke-Wulf 190 fighters. He fought them off for 10 full minutes, outclimbing one, outturning another, and managed to limp home with stable engine temperatures the entire time. After landing, Red walked straight into the hangar, looked Tex in the eye, and said, "You saved my life up there. Whatever you're doing, keep doing it." Word reached higher-ups within days, not through formal channels, but through whispers, combat reports, and pilot debriefs. Suddenly, senior officers started asking questions. Why are your planes lasting longer? Why are your engines running cooler than spec? Why are pilots requesting the same 6 tail numbers every mission? Tex knew it was only a matter of time before someone came to investigate, but by then, his small rebellion had turned into a quiet revolution. What started as an unsanctioned tweak to a single Mustang had now taken on a life of its own. Within weeks, Tex Harper's cooling modification was no longer just a rumor. It became a movement. The mechanics on the base started replicating his work, adjusting their own radiator ducts, comparing airflow results, and sharing stories over coffee and cigarettes. What had once been a hidden fix, quietly shared between squadron mates, had spread across the entire base. Tex's innovation wasn't just a fix, it was a game changer. The word spread slowly at first, in hushed conversations over lukewarm coffee in drafty hangars. But it wasn't just talk. The numbers began to show something undeniable. First, the engine temperatures. Pilots flying the modified P-51s reported a consistent drop in high-altitude engine temperature, 15 to 17 degrees Celsius lower than standard configurations. This may not sound dramatic on paper, but at 25,000 feet, that margin meant the difference between pushing the aircraft to its limits or throttling back to avoid an engine fire. Second, the time to climb. With better airflow and reduced drag through the modified radiator duct, Mustangs reached combat altitude faster, up to 12% faster, depending on loadout and weather. This gave pilots a crucial advantage, allowing them to gain altitude over their German adversaries more quickly, securing the coveted altitude advantage in air combat. Third, and perhaps most importantly, was survivability. In just one squadron, the kill-to-loss ratio for Tex-modified aircraft jumped to more than 3.1 over a period of 6 weeks. The pilots flying the planes weren't different. The guns hadn't changed. The fuel was the same. The only difference was the reshaped airflow duct and the man who dared to modify it. Soon word spread beyond Tex's original unit. Mechanics from neighboring airfields across East Anglia started writing home, asking for thin aluminum sheets, smoother tools, even homemade sealants to replicate the improvements. Some even pulled parts from grounded aircraft just to copy the internal veins. Unofficial blueprints began circulating on napkins, notepads, and even pages torn from aircraft maintenance logs. There was no central design. Each mechanic added their own touch to the concept, but all of them owed their inspiration to Tex Harper and his original rule-breaking experiment. Despite this, the top brass hadn't formally acknowledged anything. Higher commanders were aware that something was happening, but with kill ratios improving and mission success rates climbing, no one was eager to investigate too deeply. As long as the planes kept flying and the pilots kept coming home, any potential violations were quietly overlooked. That was until a visiting colonel from the 8th Air Force Command stopped by the base for an inspection. During his routine walkthrough of the maintenance operations, he spotted the belly scoop on a P-51. The aircraft had been opened for a coolant line check, and he noticed the non-standard ductwork, angled metal vanes, polished smooth, clearly not part of any authorized blueprint. His face turned red. Within minutes, he was demanding answers. Who authorized this modification? Where were the engineering documents? Why hadn't North American Aviation, the aircraft's manufacturer, been consulted? Tex was called in. He didn't lie. He calmly explained what he had changed and why. He showed temperature logs, climb rate comparisons, and combat reports. Other mechanics backed him up. Even pilots, some seasoned aces, lined up to speak on his behalf. One of them, Captain Red Lansing, stood before the colonel and said, "Sir, you can fly it cold or die hot. That's the choice." The colonel didn't respond immediately, but he made a call that evening. 2 days later, engineers from North American Aviation arrived at the base, carrying blueprints, testing equipment, and a list of questions. They spent a week examining Tex's modifications. They ran airflow tests, took detailed photographs, and even installed pressure sensors inside one of the modified ducts. When the data came back, the verdict was clear. Tex Harper's design didn't just work, it was brilliant. The internal vanes helped stabilize airflow, reduce turbulence, and increase pressure across the radiator core. That improved heat dissipation and allowed the Meredith effect to take effect under combat conditions, creating a small but measurable thrust gain. Exactly what the original designers had hoped for, but couldn't achieve under lab conditions. In short, Tex had done what a team of engineers had failed to accomplish in 2 years of development. The recommendation came quickly. North American Aviation began reviewing the modifications for inclusion in the next production batch of P-51s, the D variant, which would become the most famous model of the war. As for Tex, he wasn't reprimanded. He was promoted to technical sergeant and later received a field commendation for his innovation under combat conditions. But Tex didn't care about rank. What mattered to him was that more pilots were coming back now because of something he built with scrap metal and instinct. That was enough for him. The pilots knew who to thank. One of them even carved it into the access panel of his Mustang with a pocket knife. For Tex, who made her breathe, by the spring of 1944, Tex Harper's once secret duct modification had become an open secret across East Anglia. Dozens of P-51s now carried the internal vane system. Pilots were flying higher, fighting longer, and experiencing fewer overheating problems. But success in the shadows doesn't last forever. When the visiting colonel from the 8th Air Force Command noticed the unauthorized ductwork during his inspection, his response was swift and furious. Military aircraft weren't supposed to be modified in the field, especially not structural components like a cooling system. The rules were there to ensure consistency, safety, and accountability. Within hours, a stop work order was issued. All aircraft with modified cooling ducts were to be grounded for review. No further changes were to be made without written engineering approval. For Tex, this was more than just a slap on the wrist. His work had saved lives, but the bureaucracy of war was quick to push back against such unsanctioned innovation. The tension was palpable that night, as mechanics whispered in corners, unsure of what would happen next. Some feared Tex would be court-martialed. Others thought the entire squadron would be punished. But then something unexpected occurred. The pilots pushed back. It started with Captain Red Lansing, who walked into the command office still in flight gear and made his case directly to the squadron leader. He didn't raise his voice. He simply stated the truth. "Sir, I don't care what's written in the tech manual. Those modified planes keep us alive. You put me in a stock model, and I'm a sitting duck above 20,000 feet. More pilots followed. One by one, they stood up and spoke with quiet conviction. They weren't engineers, but they knew what worked, and the results spoke for themselves. Tex's modification worked. Under mounting pressure, the squadron leader sent a formal request to delay the grounding until the aircraft could be properly evaluated. The brass reluctantly agreed, but only if North American Aviation sent engineers to inspect the modifications firsthand. And so they did. Within days, 2 senior engineers arrived at the base, men dressed in wool coats and horn-rimmed glasses, clearly unused to the mud, noise, and urgency of a frontline airfield. They examined Tex's modified Mustangs carefully, taking measurements, asking questions, and comparing them with factory specifications. Initially, they said little, but once they ran wind tunnel simulations and pressure tests using their field instruments, their silence was broken. "This is effective," one of them finally admitted. "Very effective," the engineers confirmed what Tex and the pilots had been saying for weeks. His reshaped duct improved airflow, increased internal pressure, and provided better heat dissipation. It wasn't a fluke. It was solid engineering, even if it hadn't come from a drafting table. The engineers didn't stop at approval. They took detailed notes and sent them back to California, where North American began adapting the concept for future production models. The confrontation ended not in punishment, but in progress. Tex was called into the squadron office. The same colonel who had threatened to ground the planes handed him a typed letter. It was a commendation for field innovation, accompanied by a promotion and official recognition that his modification had saved lives. Tex didn't say much. He just nodded, tucked the letter into his breast pocket, and returned to the hangar. There were still more planes to fix and more pilots to protect. By late March of 1944, what had begun as one man's quiet act of defiance had become officially recognized. North American aviation engineers didn't just validate Tex Harper's design. They embraced it. Back in their California facilities, they began drafting formal revisions for the P-51's radiator duct system. The technical name for it would appear in memos and blueprints as an internal airflow smoothing and compression retrofit. But among the pilots and mechanics who lived through the change, it would forever be known as Tex's fix. With the release of the P-51D variant, the most famous and widely used model of the Mustang, Tex's ideas became permanent. New Mustangs rolled off the production lines with optimized duct shapes, smoother flow paths, and subtle design tweaks, all inspired by Tex's scrap metal prototype. What the engineers in suits had once theorized, a mechanic in coveralls had proven in the heat of war. This twist was unexpected. A mechanic with no formal degree, no engineering title, and no clearance to innovate had not only solved a high-altitude performance issue, but had helped reshape the most effective fighter aircraft of World War II. The Mustang's ability to escort bombers deep into Germany without overheating, to climb higher and faster than nearly any other propeller-driven plane, and to survive grueling dogfights above the clouds. All of it had been enhanced by a change that wasn't even supposed to exist. Pilots noticed the shift immediately. The new Mustangs felt tighter, more responsive in the climb, and better in high-altitude turns. Engine temperatures remained stable, even under extended boosts. In combat, this meant fewer aborted missions, fewer emergency landings, and a greater margin for survival. By the time the Normandy invasion was approaching in June of 1944, Mustang squadrons across England were flying almost exclusively with aircraft, featuring the revised cooling design. What had once been a grounded, unauthorized mod was now gospel. Tex never bragged about any of this. He didn't give interviews, didn't write reports. His name never appeared on any blueprints. But among the crews, he became a quiet legend, not because he wanted fame, but because he did what needed to be done, and he did it right. One of the younger mechanics who worked under Tex during those months recalled a moment when the first P-51D arrived on base with the new duct already installed by the factory. Tex walked over to the plane, crouched down, ran his hand along the inner curve of the scoop, and nodded. Then he simply said, "They got it." For Tex, that was enough. It wasn't about getting credit. It was about seeing that the idea, born from necessity, instinct, and a little rule-breaking, had found its rightful place in the war effort. And for the pilots, the message was even clearer. Whatever it took to stay alive, they knew who to thank. They didn't care where the fix came from. They only knew their Mustangs ran cooler, flew better, and brought them home more often. The shift from a rogue modification to an official standard was a rare moment in military history. It was a reminder that sometimes innovation doesn't come from boardrooms or labs, but from freezing hangars under the hum of engines, in the hands of men who trust what they feel more than what they're told. March 6, 1944. The U.S. 8th Air Force launched its boldest daylight bombing mission yet, Berlin. The heart of Nazi Germany, home to its power, industry, and propaganda. The Germans knew it was coming. They prepared to throw everything they had into the sky to stop it. Hundreds of American B-17 Flying Fortresses and B-24 Liberators took off from bases across England, targeting the industrial and military facilities around the German capital. Their protection: squadrons of P-51 Mustangs, soaring high and fast as fighter escorts. For weeks, Tex Harper's modified Mustangs, and now their factory-built successors, had been proving their worth. But no test was more significant than the airspace over Berlin. It was the most heavily defended air corridor in Europe. The Luftwaffe stationed their best squadrons along the route, experienced pilots, aggressive tactics, and swarms of fighters, mostly Focke-Wulf 190s and Messerschmitt Bf-109s. The mission's early hours were eerily quiet. The bombers droned eastward in tight formation, silhouetted against a cold blue sky. But just west of Berlin, the Luftwaffe struck. German radar picked up the American force, and waves of fighters scrambled. Their plan was simple: hit the bombers hard and fast before they reached Berlin, and do it above 25,000 feet, where cold temperatures would test both engines and nerves. But this time the Mustangs didn't fall behind. They didn't lag, overheat, or break formation. They stayed up and hit back. In the chaos that followed, dozens of dogfights erupted across the sky. Mustang pilots dove and climbed with precision, executing tight turns and slashing attacks that tore through German formations. They no longer had to worry about managing engine temperatures during combat. They could stay in the fight longer, and with that came a newfound aggressiveness. Captain Red Lansing, flying one of Tex's early field-modified Mustangs, reportedly scored 3 kills that day, 1 Messerschmitt and 2 Focke-Wulfs in a 10-minute stretch near Potsdam. After landing, he said, "The engine didn't even flinch. I was climbing at 30,000 feet and still had power left. They tried to outclimb me and they couldn't." Other pilots reported the same. One group credited the cooling system improvements for allowing extended high-power climbs that would have been impossible just months earlier. No overheating, no boil-off, just raw, reliable power. By mission's end, 69 German aircraft had been confirmed destroyed, and many more were damaged. The Luftwaffe had been dealt a blow it couldn't recover from quickly. And most remarkably, nearly every American bomber made it home. The Berlin raid didn't just strike fear into the heart of the Reich. It proved that the US now had air superiority, even over the most heavily defended city in Europe. And while the headlines back home praised the courage of the pilots and the precision of the bombers, few knew what had really made that mission possible. It wasn't just the Merlin engine, the fuel tanks, or the combat training. It was airflow. It was cooling. It was the ability to fight at 30,000 feet without your plane turning against you. And for that, the credit went to one man, Tex Harper. That day over Berlin marked a turning point. Not just in the war, but in how air combat was fought. It was no longer enough to have speed or firepower. You needed reliability, altitude, and the edge. And thanks to Tex, the P-51 Mustang had it. After Berlin, the air war changed. The Mustang, already respected, became feared. German pilots began to recognize its silhouette instantly and dread it. The P-51 was no longer just a fast escort. It was a predator, a high-altitude killer, a plane that could fly farther, climb faster, and fight longer than anything the Luftwaffe could throw at it. The secret to that leap wasn't some high-level strategy session or a factory breakthrough. It was a mechanic with a hacksaw and a cold hangar who refused to accept good enough. Tex Harper never appeared in the headlines. He didn't give interviews or claim credit. After the war, he returned to Oklahoma and opened a small engine repair shop. Most of his customers never knew he had once shaped the sky over Europe. But his legacy didn't end in 1945. The principles behind his cooling mod, the practical application of the Meredith effect, became standard in post-war aircraft design. Engineers studying jet propulsion borrowed lessons from Tex's battlefield ductwork. The idea that cooling systems could contribute to thrust, not just manage heat, carried forward into the jet age. In the Korean War, American jets, like the F-86 Sabre, benefited from refined airflow engineering that traced some of its roots back to what Tex proved in the field. Even modern stealth fighters, with their carefully managed heat signatures and internal ducting, owe a technical debt to what happened beneath the fuselage of a P-51 Mustang in 1944. But perhaps the most enduring legacy wasn't found in blueprints or museum plaques. At the National Museum of the United States Air Force in Dayton, Ohio, there's a restored P-51 Mustang painted in the colors of the 8th Air Force. It's a beautiful machine, shining aluminum skin, invasion stripes on the wings, and the name Lucky Lady stenciled beneath the cockpit. If you crouch down and look beneath the belly, just inside the edge of the radiator scoop, you'll see something most visitors miss. 3 words etched in small, careful letters, for Tex, who made her breathe. No ceremony, no statue, just a quiet acknowledgement from one generation of warriors to the man who helped them survive. And that's the kind of legacy that outlives medals. They say history is written by the victors, but sometimes the most important parts are written in grease, not ink, in silence, not speeches. Tex Harper never fired a gun in combat. He never pulled G's in a dogfight or bailed out of a burning cockpit. But without him, a whole generation of pilots might not have made it home. He broke the rules. He ignored procedure. And in doing so, he saved lives. Not through force, but through focus. Not through orders, but through understanding. He saw a problem, and instead of waiting, he fixed it. That's not just engineering. That's courage. Lieutenant Jack Reynolds, the pilot we met at the beginning, once gave an interview years after the war. He was older then, white hair, a quiet voice. When asked who his hero was, he didn't name a general or another pilot. He said this: "People talk about aces, but the man who saved my life wore oil-stained coveralls and never left the ground. I don't even know if I ever saw his face. But I remember how that engine held together when I needed it most. He gave me altitude, and that gave me a chance to come home." There are thousands of stories like that from the war. Stories that were never told or were nearly forgotten. Stories that remind us that victory isn't just about firepower or bravery in the sky. It's also about people like Tex, the ones who work quietly, solve problems and build things better, not because they're told to, but because it's right. Not all heroes fly. Some kneel under a Mustang in the dead of night, shaping aluminum with frozen hands, thinking about the pilot who will sit behind that engine tomorrow. And thanks to Tex Harper, that pilot had a better chance of coming home.